Coming to introduction, in this progressive world, the device scaling memories has become cheaper, faster and more efficient. According to ITRS, International Technology Roadmap for Semiconductors, memories will be having a dominating presence in SoCs. Also, the transistor packing densities of memory is not only higher but also faster than compared to logic circuits. Most of the signal processing systems majorly require filters, and we know that these filters contains multipliers that perform the multiplication operation. During this process, we will be using our lookup tables. Let's see how a conventional lookup table multiplier will be something like this. It contains address ports, it do contain an output port, with an input x of length L bits and the multiplied coefficient factor Ax at the output. For L length of input, there exists 2 per L memory locations. 2 per L memory locations. So, let me take the input some 001011, which is of 5 bit. So, total number of memory allocations will be 2 per 5, which is nothing but 32 different memory is to be allocated. That is what this is mentioned here, starting with 1, 2, 3, 4, 5, 6, 7 till 31. This is the major drawback of using LUTs, that is, it occupies more size. This can overcome by implementing LUT techniques, nothing but anti-symmetric product coding and odd multiple storage approach. The third is the combine approach, where I will be combining anti-symmetric product coding as well as odd multiple storage. With respect to anti-symmetric product coding, if I am taking the same example, that is 00100, which is of 5 bit input, if you could observe here, the same 32 different locations are being bifurcated into 2, starting with 1 to 16A, again back from 16A to followed by 31A. If you could observe here 00100, where is the combination here? 00100. For this, if I am making a 2's complement, 00100, its 1's complement will be 11011 plus 1, 110 with the carry 1, 110 with the carry 1, 01111. So the solution for the 2, this is the 2's complement representation. It is 11100. So this is what I am getting. You can observe here, any of the input that you are taking, its 2's complement will be the replicate of this part. Let me take one more example here, 01100, 01100. For this, the 1's complement will be 10011 plus 1, I need to make it a 2's complement, 110 with the carry 1, 110 with the carry 1, 0101, so output is 10100. You can see here, the output is 10100. Thereby, instead of storing all this 32 into 32 different memory locations, I can able to store only the address values, for which I can retrieve the remaining values. In this figure, you can observe the circuit is designed that compresses the 5 bit input to a 4 bit and sends it to the memory array. See here, this is my first input, second input, third input, fourth input, and this is my 5th bit, followed by this is the main part, this is my MSB here. Because of this compressor, I will be able to compress this 5 bit to 4 bit representation, first bit, second bit, third bit as well as fourth bit. Since this is a 4 bit, I will be allocating here 2 per 4 memory locations. Instead of 2 per 5, I am drastically reducing it to 2 per 4 memory locations. Thereby performing an addition as well as subtraction operation based on the sign value. Sign value represents my MSB here. Based on this sign value, I am going to perform the anti-symmetric product coding operation. If you could observe here, my product word is equals to 16A plus sign value into APC word. 16A is nothing but a constant factor, and this sign value is represented by my MSB value. If the value of MSB is 1, I will be considering -1 as sign value, and if it is 0, I will be considering +1 as my sign value. so that if I am making a product of with APC1, I am going to retrieve my remaining values. You can see in that next slide. Let me take the example of this factor 00010. Now what is my product value? Product value is equals to 16a plus sign value plus APC value, isn't it? So 16a plus sign value, since the MSB of this part is 0, a minus 1 sign value is being considered plus APC value, and what is the value which is being stored here? Nothing but 14. Yes or no? Since it is in second position, I am taking the second position value, nothing but 14. So that 16a minus 14, I am going to get it as 2a, which is my this value. Similarly, if I am talking with respect to this, since the MSB is 1, I will be taking my product value 16a plus sign value now becomes positive because the MSB is 0 here, plus APC1, which is nothing but 14. So that I will be getting 16a plus 14a, which is nothing but 30a. I am going to retrieve this value. Thereby, if you can observe here, instead of storing 5-bit data, I am just going to store this address values and I am going to retrieve the remaining values. Let me take one more example. Let me take the example of this one. Here the MS value is 0. Since the MS value is 0, I am taking the product value is equals to 16a plus sign value will be minus 1 since the MS value is 0 plus what is my address value which I am going to store, that will be 2a. So I am retrieving 2a. So the value will be 16a minus 2a, which is nothing but a 14a. This is what I am going to get. If I am talking with respect to this, here the MSB value is 1. So I need to take a positive sign. PA is equals to 16a plus 1 plus 2a, and the value will be I will be getting is 18a, which is nothing but this value. Thereby, instead of storing these 32 different memory locations, I can reduce it to 4-bit storage where I will be using only 16 memory location and I can change the address values and then I can further forward it.